Okay, so in the last section we were looking at finding series solutions for second order homogeneous linear DEs about what we were calling ordinary points. And we talked about the difference between an ordinary point and a singular point. In this section, we're going to look at what it looks like to take or to find series solutions for these DEs about a singular point. And in particular, we're going to be working with the singular point x equals 0. Even though this applies to the more broad case of any singular points satisfying certain conditions, our examples are all going to involve the singular point that we're finding our power series about. It's going to be 0. So once again, we're working with second order linear homogeneous DEs that have been put into this form, where if we have some coefficient on the y double prime term other than 1, we divide everything by that, so that this is just y double prime. And then we're going to refer to these two functions as p of x and q of x. So the first thing we need to talk about is certain classifications for these things that we're calling singular points. There's two different classifications that we use, regular and irregular. So let's suppose, for example, that we have this DE and it has the singular point x equals x naught. We say that that singular point is a regular singular point if two conditions are met. First of all, if the function little p of x, which we define to be equal to x minus that singular point x naught times big P of x, this guy, and if q of x times or is equal to x minus x naught squared times big Q of x are both analytic at x naught. So basically multiplying p of x by x minus x naught and q of x by x minus x naught squared, if those two products produce analytic functions, then we refer to the singular point x naught as a regular singular point. Okay, and if this doesn't happen after doing these multiplications, then we say that it's an irregular singular point. Now I want to think about what this condition implies. Suppose, for example, that x naught is a singular point because maybe x minus x naught shows up as a factor in the denominator of p of x. If p of x is a rational function and in its denominator we have x minus x naught, then that function would not be defined at x naught, and that's part of the reason we would have a singular point at x naught. But then multiplying that function by this, x minus x naught, if it cancels that only factor of x minus x naught out, then we've essentially removed that singularity and we have an analytic function now. That's kind of the idea there, is that these products are supposed to cancel out factors in big P of x and big Q of x that are causing x naught to be a singular point in the first place. So let's take a look at an example. We want to classify the singular points of this DE right here. We have x squared minus 9 squared, quantity squared, x double prime minus x plus 3y prime plus 8y equals 0. So the very first thing that we need to do is we need to put this in the correct form. So we need to divide everything by x squared minus 9 quantity squared. And if I do that, I get y double prime minus x plus 3 over x squared minus 9 quantity squared, y prime, plus 8 over x squared minus 9 quantity squared, y equals 0. So we divided by that leading coefficient there. Next thing I want to do is identify what p of x and q of x are. So p of x in this case is negative x plus 3 over x squared minus 9 quantity squared. And let's go ahead and do some factoring here to see if anything simplifies. Negative x plus 3 over, this is the same thing as x plus 3 squared times x minus 3 squared. Okay, q of x is this guy, 8 over x squared minus 9 quantity squared, which also factors. It becomes 8 over x plus 3 squared times x minus 3 squared, okay? And so again, we can identify some singular points here, and they're going to come from any places where p of x or q of x are not analytic. And we talked about in the previous section how when you're dealing with rational functions in particular, those functions are only ever not analytic at points that are not in their domain. And essentially all that means is that we look for where the denominators would equal 0. I can see that it's plus or minus 3 where that occurs. Okay, so now, so our singular points, let me write this out. Singular points for this guy are x equals plus or minus 3. So now we have to determine of those two singular points, which, if any, are regular and which, if any, are irregular. So now what we do is we take a look at these functions little p and little q that I've defined here and here, or we've also defined up here, and look at whether or not those functions are analytic at each of these singular points. So let's look at p, for example. P of x is defined to be equal, let's start by looking at the singular point x equals positive 3. Okay, so this would be x minus 3 times p of x. Now here's my p of x right here. So that x minus 3 is going to cancel with, oh, actually, let's do this too. I should do some cancellation here. So I'm going to squeeze this in. This is the same as minus 1 over x plus 3, x minus 3 squared. Okay, because I do have that x plus 3, that common factor that can factor out there. So x minus 3, if I multiply this function by x minus 3, then this x minus 3 will cancel with one of those x minus 3's, giving me negative 1 over x plus 3, x minus 3. Okay, now this function, even after multiplying p of x, big P of x, by x minus 3, still has an x minus 3 in its denominator. And so that means that little p of x is also undefined at the singular point 3, which means that this function is not analytic at 3. So having already determined that little p of x is not analytic at the point 3, I don't need to go and check q of x. We already know that x equals 3 is irregular. That's an irregular singular point. So let me go on and check x equals negative 3. Okay, so what is p of x equal to? Well, in the case of the singular point negative 3, we're multiplying big P of x by x plus 3. Okay, looking at p of x, which we simplified up here, there's only one factor of x plus 3 showing up in its denominator, and so multiplying that by x plus 3 will completely cancel that out. I get negative 1 over x minus 3 squared. Okay, now negative 3, when substituted into this expression, is defined. And so negative 3 does belong to the domain of little p of x, which, for, again, rational functions, implies that this point, or that the function little p of x is analytic at that point. We also need to check q of x. And for q of x, remember, we're taking x plus 3 and squaring it, then multiplying it to big Q of x. Now, here's big Q of x after simplifying, and you can see I have a factor of x plus 3 squared in there, which will cancel with that guy after doing that multiplication. I get 8 over x minus 3 quantity squared. Notice here as well, negative 3 is in the domain of this function, which makes this function analytic at negative 3. So in that case, we can say that both of little p and little q are analytic at the point x equals negative 3, so that makes x equals negative 3 a regular singular point. Okay, so that classifies those two singular points. Now, the method that we're going to be talking about in 6.3 is going to only work when we are trying to find series solutions to these DEs about a regular singular point. The method doesn't work for irregular singular points in general. It's only going to work for the regular case. Okay, so let's talk about what our method is going to look like, and then we'll start working on a solution. So in order to find a power series solution to a linear homogeneous second order DE about a regular singular point, which we just defined, we're going to use this theorem. We're not going to prove this theorem. It's beyond the scope of this class, but we will be using it. We call this Frobenius's theorem, or the Frobenius method is a term I'll use also. So if x equals x naught is a regular singular point of the differential equation, it says 1 because this was copied out of your book, but it's referring to this guy after putting that DE in the standard form like this. Then there exists at least one solution of this form. Now, notice, let's start here. So ignoring this factor right here for a second, this sum is a power series centered at x naught. It's a power series about x or in x minus x naught, that singular point that we're referencing. But then we're taking that power series and we're multiplying it by another factor of x minus x naught raised to some unknown power. And that lowercase r that's being used as the power there does not need to be a positive integer. Notice, in this summation, n is always going to be some non-negative integer because it's it's the index. It comes from the index for our summation, so n equals 0, 1, 2, 3, 4. It only takes on non-integer values. I'm sorry, non-negative integer values. R can be literally any real number. It can be negative, it could be irrational, it could be rational, it could be anything. But it is going to have specific values that we have to find when we're trying this method, okay? So this series can be simplified by bringing this factor in to that sum right there, and we get the sum from n equals 0 to infinity of Cn x minus x naught to the power of n plus r once we do that. And again, it says where r is a constant to be determined. And then the theorem guarantees that the series will converge at least on some interval bounded by x minus x naught is between 0 and capital R. And remember that capital R we talked about in the previous section, it's that minimum radius of convergence. It's that value that represents the smallest distance between that ordinary, let me back that up. That capital R is the same thing that we were using back in section 6.2. The important part, though, is what this series looks like and the fact that R does not have to be a non-negative integer. So I'm actually going to do this in the next video. I'm going to run through an example where we use Frobenius's theorem to solve a second order DE about a regular singular point. But let's do that in part 2.